Hello everyone. From the last couple of sessions, as you all know, we have been solving problems based on logical instructions. So welcome to the session, Logical Instructions Solve Problem 3. Without any further ado, let's get to learning. Coming to the topic that we are going to cover in this session, today we are going to solve another problem on logical instructions of 8085 microprocessor. Consider the question. We are supposed to assume that before execution of any instruction, we have within the accumulator the value 65H. Then within the general purpose register B, we have got the value B2H. Within H register, we have got the value F9H. Within the general purpose register L, the value has been loaded as 50H. The carry flag is set to 1. And the content of the memory location F950H is 38H. Now we are supposed to find out what is the value of the accumulator register and the value of the different flags after the execution of the following instructions. As you can notice, we are going to execute 7 different instructions. Now before we begin, let's load the values in their respective locations. So let me highlight all the values that we have in the question. As it mentioned in the question, within the accumulator, that is the A register, we are supposed to load the value 65. Remember, all the values that we will be loading are going to be hexadecimal values. Now coming to the B register, we are supposed to have the value B2H. So let's load that as well. In the general purpose register H, we will have the value F9. And in L, we will have the value 50. So let's load them as well. Now notice one thing. We already know the value that the HL register pair holds is generally referred to as the memory location, which is supposed to be pointed by this HL register pair. Now notice the content of the HL register pair, F950. And it has already been mentioned in the question. In the location F950, we are supposed to load the value 38H. Therefore, in the memory location F950, we will have the value 38H. Now let's proceed ahead and execute this instruction CMP B. Now if you remember, the instruction CMP B falls under the instruction type CMP R. Now what does this instruction do? Using the instruction of this type, we generally compare the value within the accumulator register and the value which will be specified by this R. Now when we use the capital R within the instruction type, you already know we are talking about the accumulator, all the 6 different general purpose registers, as well as the memory location which is supposed to be pointed by the HL register pair. But if you notice in the instruction that we have got, it is CMP B. So we are supposed to compare the value within the accumulator register with the value stored inside the general purpose register B, that is B2H. Now how this comparison is performed? I hope you remember the microprocessor in this case uses the subtraction operation. So basically the value B2 is going to be subtracted from the value 65. So when the microprocessor will execute the instruction CMP B, in the subtraction, the minuend is going to be 65H and the subtrahend is going to be B2H. Now in the previous sessions we have already discussed that in the 8085 microprocessor, we don't really perform subtraction. Rather, the subtraction is performed using addition, and for that, we use the 2's complement approach. Now since here we are using hexadecimal digits, we will use the 16's complement approach. So clearly, we need to find out the 16's complement of B2. Now how to do that? You already know this. The least significant digit, that is 2, we will have to subtract it from 10 of hexadecimal. And the most significant digit, that is B, it will be subtracted from F. So let's do that now. From 10, that is 16 of decimal, if we subtract 2, we are supposed to get the value 14, which in hexadecimal is E. Now the most significant digit, that is B, is supposed to be subtracted from F. Now F is 15, whereas B is 11. So the result of the subtraction will give us the value 4. Therefore, The 16th complement of B2 is 4E. Now we can proceed ahead with the addition. With 5 we are supposed to add E. We may use the shortcut approach in here. If from 5 we take out 1 and add that 1 with E, E is going to become F and 5 will be 4. Now adding any value with F in hexadecimal, as the sum we will get 1 less than the value, so we will have 3 in here. Also, there will be a carry. Now notice, with 1 we are supposed to add 6, which will give us 7. And 7 plus 4 is 11, which in case of hexadecimal is B. Now think about it. We are executing the instruction CMP B. Since this is comparison operation, the result is not going to be updated inside the accumulator. And the reason for that is, we just want to compare these values. We don't want to alter them. And that's the reason we will use the temporary register of 8-bit to store the values. Now 3 of hexadecimal in 4-bit binary is 0011, whereas B, which is 11 in case of decimal, in 4-bit binary it is 1011. Now let's check what will be the bits inside the flags register. As you can notice, while performing this subtraction using 16th complement approach, we didn't generate any carry. And this means that the value which has been generated is a negative value. Now since we perform subtraction, the carry, which in this case is 0, is going to be fed to the carry flag via the inverter. So 0 will set the carry flag. Now what about the parity flag? You already know it will be set if in this particular case within the temporary register we have got even number of ones. Now do we have that? Let's check. 1, 2, 3, 4, 5. So we have got 5 ones. That's an odd number. So the parity flag will be reset. What about the auxiliary carry? Well, we did generate a carry from the addition of the least significant digits. So yes, the auxiliary carry flag will be set. Let's talk about the Z flag now. 0 flag is supposed to be set if within the temporary register we have got all zeros. We don't have that, right? So the 0 flag or the Z flag will be reset. What about the sign flag? If you notice within the temporary register, the most significant bit is 1. So the sign flag will be set to 1. Now notice, we the humans, looking at the values 6, 5 and B2, can directly say that the value within the B register is greater than the value of the accumulator. But the microprocessor doesn't know that, right? And for that, it will use the status of the flags. Notice, in all these cases, we are supposed to consider the carry and the 0 flag. Now what is the status of the carry flag here? It is 1. And what's the status of the Z flag? It is 0. Now when carry is set and the Z flag is reset, it means the accumulator's value is lesser than the B register, which indeed is correct. Now we were not supposed to find this. We were supposed to find the value of the accumulator and the status of different flags within the flags register. So after the execution of the instruction CMP B, since for the result we are using temporary register, the value within the accumulator register will remain intact. However, the flags register's content will be affected. As you can see, CY flag is set, parity flag is reset, auxiliary carry flag is set, then Z flag is reset, and the sign flag is set. So we are done with the first instruction, CMP B. Let's now focus on the next instruction, CMP M. Now you already know, using M, we generally refer to the memory location which is currently being pointed by the HL register pair. Now what value do we have in there? It is 38. Therefore, execution of the instruction CMP M is going to compare the value of the accumulator register, that is 65, with the value within the memory location F950, that is 38. So we are supposed to perform the subtraction between 65 and 38. You already know this. We have to find out the 16th complement of 38, and for that, 8 will be subtracted from 10, that is 16, and 3 is going to be subtracted from F, that is 15. Now if we subtract 8 from 16, we will get the result 8, right? And if from F, that is 15, we subtract 3, we will have the result 12, which in hexadecimal is C. Therefore, the 16th complement of 38 is C8. Now we can go ahead and perform the addition. With 5, if we add 8, the value in decimal is 13, which in case of hexadecimal is D. Now notice we are supposed to add 6 with C, that is 12 of decimal. So the value is going to be 18. Now 16 of decimal is 10 in hexadecimal, therefore 17 is 11 and 18 is 12. So if we add 6 with C, we will have the result 12. Now notice, we performed the subtraction of two 2-digit hexadecimal values, but we received a 3-digit result. We already know what will happen. Since the instruction CMP M is being executed, the result is going to be updated within the 8-bit temporary register. And we are supposed to store the least significant 2 digits 8-bit equivalent binary. So D, since it is 13 of decimal, in 4-bit binary it is going to be 1101. What about 2? Pretty simple. In 4-bit it is 0010. Let's now see the flags register's content. Since we have generated a carry and we know we performed subtraction, so this carry is going to be fed to the carry flag through the inverter or the NOT get. So the status of the carry flag will be reset. And this means that the subtraction that we performed gave us the result of a positive value. Now let's talk about the parity flag. Notice the contents within the temporary register. How many ones do we have here? 1, 2, 3, 4. Now 4 is an even number. Therefore, the parity flag is going to be set. What about auxiliary carry flag? During the addition, no carry was generated from the addition of the least significant digits. Therefore, auxiliary carry will be reset. What about the Z flag? Within the temporary register, we don't really have all zeros. Therefore, Z flag will be reset as well. Coming to the sign flag or the S flag, if you notice, within the temporary register, the most significant bit is 0. Therefore, the sign flag will be also reset. Now notice, we executed the instruction CMP M, which falls under the type CMP R. Now looking at the values 65 and 38, which was stored inside the memory location F950, which is currently being pointed by the HL register pair, and we use that location using the indirect register addressing mode, that is M. Anyway, since we are comparing two values, we are supposed to check for the flags carry and Z. Now in this particular case, the carry flag is reset. What about the Z flag? It is also reset. This dictates the situation 1. That is, the contents within the accumulator register is greater, and which is correct, because 65 of hexadecimal is definitely greater than 38. Therefore, after the execution of CMP M, the value within the accumulator register will be intact. However, the bits of the flags register is going to be altered based on the contents of the temporary register. So the carry flag will be reset, parity flag will be set, and the flags auxiliary carry Z and the sign, all of them will be reset. So we are also done executing the second instruction CMP M. Let's now focus on the third instruction CPI 55H. As you can notice, this is the instruction where we are using immediate addressing mode. We are sending the second operand via the instruction itself. So, with the content of the accumulator, which is 65, we are going to compare the value 55. Let's perform the subtraction. The minuend is 65 And the subtrahend we are sending directly, that is 55. Let's find out the 16's complement of 55. From 10, that is 16, if we subtract 5, we will have the result as 11, which in hexadecimal is B. Then from F or 15, if we subtract 5, we will have the result as 10, which in hexadecimal is A. So the 16's complement of 55H is ABH. Let's now perform the addition. With 5 we are adding B, that is 11 in decimal, so we will have the result as 16, which in hexadecimal is 10. So we will get the sum as 0 and the carry will be 1. Now with 6 we will add 1, so we will have 7, and 7 thereafter will be added with A, which in case of decimal is 10. So the result is going to be 17 of decimal, which in hexadecimal is 11. I hope you get this point. Since 16 of decimal is 10 of hexadecimal, so evidently 17 of decimal is going to be 11. So adding all these 3 digits, we will have the result as 11. Now the least significant digits equivalent 8-bit binary we will store within the temporary register. Now 0 is 4 zeros in binary and 1 in 4-bit binary is 000 followed by 1. Let's talk about the flags register now. We generated a carry, which means the result is a positive value. And this carry will be fed to the carry flag via the inverter. So the carry flag eventually will be reset. What about the parity flag? Since within the content of the temporary register, we have got a single 1, that means we have got odd number of 1s, so the parity flag is to be reset. Coming to the auxiliary carry, yes, from the least significant digits addition, we generated a carry, and this is the auxiliary carry, so it will be set. What about the Z flag? Notice, within the TR register, we have got a single 1, that means all of them are not zeros. So the Z flag will be reset as well. Now coming to the S flag or the sign flag, since the most significant bit in here is 0, therefore sign flag will also be reset. Now can you tell me which value is greater? Well, we are human beings and we can directly say 65 of hexadecimal is definitely greater than 55, but can the microprocessor figure it out? Well, for that we will need this chart. We executed the instruction CPI55H, which falls under the instruction types category CPI-D8. And if you notice, here the carry flag is reset as well as the Z flag. And this indicates the situation 1, that is, the value within the accumulator is greater than the immediate 8-bit data. So after the execution of CPI55H, within the accumulator register, we will still have 65. However, the flags register's content will be affected. So CY flag is to be reset, and the same can be stated for parity, Z or 0, and the sign flag. Only the auxiliary carry flag is going to be set. With this, we have also seen the execution of CPI55H. Let's now focus on the fourth instruction, that is RAL. Now RAL stands for rotate accumulator left involving the carry flag. So the carry flag which was set previously is going to be used now. Now we will need this organization to execute this. If you notice, within the accumulator, we have got the value 65. Now 5 in 4-bit binary is 0101. What about 6? In 4-bit binary, it is going to be 0110. Now the carry flag initially is set, so we will also set the carry flag. Now if we execute the instruction RAL, the most significant bit within the accumulator, which is 0, will come out and it will be placed within the carry, making the carry bit come out of its place. Now all these rest of the bits within the accumulator will be shifted towards the left by 1 bit. And finally this bit 1 will be placed as the least significant bit. Now notice, after the execution of the instruction RAL, within the accumulator register, we have got the 8 bits as 1100 followed by 1011. Now 1100 is 12 of decimal, which in hexadecimal is C, and 1011 is 11 of decimal, which in hexadecimal is B. So after the execution of the RAL instruction, within the accumulator register, the value which was previously 65 will now be converted to CB. And the status of the carry flag, which was initially set, will now be reset. Always remember, RAL is going to involve the carry flag while performing the rotation. With this, we have also executed the fourth instruction. Let's now focus on the fifth instruction, RRC. Now RRC stands for Rotate Right Accumulator and send a copy of the least significant bit to the carry flag. Remember, we are not supposed to involve the carry flag. So we need this organization to execute the instruction. Within the accumulator, we have got the value 65. The 4-bit binary of 5 is 0101. And the 4-bit binary of 6 is 0110. And initially the carry flag is set. So let's set that. Now we can go ahead and execute the RRC instruction. The execution of the RRC instruction will bring the least significant bit, that is 1 in this case, out. And we are also supposed to send a copy of this to the carry flag. So the carry flag will again be set. Now we can shift all these 7 bits towards the left by 1 bit. This will make a space at the most significant bits place. So the least significant bit, which was 1 previously, will now become the most significant bit. Now notice, within the accumulator, we have got the 8 bits 1011 followed by 0010. 1011 in hexadecimal is B and 0010 in hexadecimal is 2. So the contents of the accumulator register is going to be B2. And the carry flag, which was previously set, will be in the same state because the least significant bit of the hexadecimal value 65 was 1. Therefore, carry flag, which was previously set, will still be set. With this, we have also seen the execution of the fifth instruction RRC. Let's now focus on the next instruction, that is CMA. Now I hope you remember that the instruction CMA stands for complement the contents of the accumulator. Now within the accumulator, we have got 65, that is 0101, which is 5, and 6 is 0110. Now execution of this instruction CMA will complement the contents of the accumulator. Let's focus on the least significant nibble at first. 0101, if complemented, will become 1010. What about the most significant nibble? 0110. So complementing it, we will have the value 1001, right? Now observe, 1001 is 9 and 1010, which is 10 of decimal, in hexadecimal is A. So after the execution of CMA, since previously we had the 65 value within the accumulator register, the new updated value within the accumulator is going to be 9A. And you already know, CMA instruction doesn't affect any of the flags register. With this, we are done with the sixth instruction. Let's now focus on the seventh instruction, that is CMC. It is pretty simple. As you can notice, we are only to complement the content of the carry flag. Now carry flag initially was set, so it is set before the execution of CMC, and after the execution of CMC, it will be reset, right? With this, we have completed all the instructions that we were supposed to execute. So in this session, we solved a problem on logical instructions. Alright people, with this session, we have come to an end of the chapter 3, that is Instructions of 8085 Microprocessor Part 1. From the next session onwards, we will begin our fourth chapter, Instructions of 8085 Microprocessor Part 2. So I hope to see you in the next sessions. Thank you all for watching.